Hello everyone, and welcome back. Last time we finished focusing on rotational motion, and today we're going to start looking at section 11, gravity, which we'll actually see is going to involve looking back at a number of things from rotational motion. What I'd like to do is start out by talking about a couple of extremely important astronomers in the development of the theory of gravity, and then we'll talk about one more in just a minute. The first is Tycho Brahe. Tycho lived from 1546 to 1601. He was a Danish astronomer, and he was very interested in astrology and making predictions in terms of where the planets are and things like that at different times. He is considered to be the greatest naked eye astronomer. Since that time, since Tycho's time, shortly afterwards, the telescope developed into the great astronomical instrument that it is now, or it started to be developed and became an incredibly important astronomical instrument now, so that basically all the important observations are done telescopically and not with naked eye. But Tycho did everything with the naked eye with an incredible array of naked eye instruments that he had built in an observatory called the Uraniborg on the island of Hven, just off the coast of from Copenhagen. Tycho hired a mathematician by the name of Johannes Kepler, who was a little bit younger than him. He lived from 1571 to 1630, and he hired Kepler to work on his data, to try and develop some mathematical theories about the positions of the planets. Tycho actually believed in a geoheliocentric model where the Earth was at the center of the cosmos and the sun went around the Earth and then the planets went around the sun, but the Earth was at the center of the cosmos. Kepler was a committed Copernican. He believed in the Copernican theory, the Copernican model of the cosmos, which put the sun at the center and had all of the planets going around the sun. With the help of Tycho's data, Kepler came up with three very important laws called Kepler's laws of planetary motion that describe the motions of the planets around the sun. What I'd like to do now is to take a look at those three laws. Kepler's laws of planetary motion state, number one, sometimes called the law of ellipses. All planets move in elliptical orbits with the sun at one focus. In other words, the planets orbit around the sun in the shape of an ellipse, and the sun is at one focus of the ellipse. If you remember, an ellipse has 2 points inside, which are very important, called the foci. Two of the plural of focus is foci. So each ellipse has 2 foci, and the sun is at one of those foci. That's the first law, law of ellipses. Second law, sometimes referred to as the law of areas, or the law of equal areas. A line joining any planet to the sun sweeps out equal areas in equal times. This tells us something about the speed of the planet as it goes around the sun. In an ellipse, sometimes the planet will be closer to the sun, sometimes it's farther from the sun. But it sweeps out, the line from the planet to the sun sweeps out equal areas in equal times. Ultimately, what this means is that the planet must travel faster when it's close to the sun, slower when it's farther from the sun. Exactly what all of these mean we'll come back to shortly. The third law, sometimes referred to as the harmonic law, is the square of the period of any planet is proportional to the cube of the planet's mean distance from the sun. Basically, what this is telling us is that the farther the planet is from the sun, the longer it takes to go around the sun. In other words, the amount of time for one complete revolution is longer the farther it is from the sun. We can state this basically as p squared equals c times a cubed, where c is a constant, p is the period of the planet, a, the mean distance from the planet to the sun, sometimes called the semi-major axis. We'll come back to that. Where c, the constant, is equal to 1 year squared divided by an astronomical unit cubed. And an astronomical unit is the mean distance of the Earth from the sun. It's semi-major axis. Okay, these results of Kepler's were all phenomenological. In other words, they just explain the motion. What do the motions of the orbits look like? There was no attempt, or, well, Kepler couldn't explain, I shouldn't say there was no attempt, he couldn't explain why they were like that. It actually took the development of another physicist by the name of Isaac Newton, who we've seen before, where he developed his universal law of gravitation. So what I'd like to do is take a look at that. Newton's law of universal gravitation is about gravity, the gravitational force. But what about universal? Why is it universal? Well, this law combined the motions in the heavenly sphere, so to speak, the celestial realm, and those down here on Earth, the terrestrial realm. So what Newton did was join together the celestial realm and the terrestrial realm in what previously had been considered a cosmos, or good order, into a universe, or a single order. So that by joining the heavens and the earth, he showed that one law, or the same laws, govern the motions not only on the earth, but also in the sky as well. What is Newton's law of universal gravitation? First, it states that any two objects in the universe have a force of attraction between them. In other words, this object, we'll call this object 1 and this object 2. Object 1 exerts a force on object 2, an attractive force. In other words, it is directed toward object 1. This we'll call F sub 2, because it's the force on object 2, but then F sub 2 1 because it is the force resulting from, or due to, or caused by object 1. So this is F21, the force on object 2. Object 2 creates an attractive force on object 1, also toward object 2. We'll call this one F1 because it's the force on object 1, and sub 2 F12 because it is due to or caused by object 2. There we go. So we have attractive forces on both objects. These forces are equal and opposite. So F12 is equal to the negative of F21, which we would hope, because we would expect Newton's law of universal gravitation to also satisfy Newton's third law of motion, which states that any object that exerts a force on another object has an equal but opposite force, etc., etc. We've seen that before. We would expect the law of gravitation to agree with that as well. So we find, yes, F12 is equal to negative F21. The magnitude of the force, now since they both have the same magnitude, okay, so the magnitudes are the same, the negative sign comes in from the direction. So this is telling us the direction is opposite. Because the magnitudes are the same, I'm not going to distinguish between one or the other. I'll just call both of them F. The force is proportional to the mass of object 1. So let's call this M1. The force of attraction between both of them is proportional to the mass of object 1. It's also proportional to the mass of object 2, so M2. And it decreases as the length between them increases. I'm going to call the distance between them R. Now, what does this mean? What does the distance between two objects mean if we've got macroscopic objects? So rather than a point particle, what if these are two extended objects? Well, it turns out that it's the distance between their centers of gravity, or for our purposes, we'll just call it the center of mass. To be more general, just the center of the object. So very qualitatively, let's just imagine it's measured from center to center. So R is the distance center to center. Okay, exactly where that point is, we won't worry about that at the moment. But we did see it before when we were talking about center of gravity. For us now, we'll just call this center to center. And it then decreases as the distance inversely, but not just inversely with the distance, it's actually the distance squared. So the force is proportional to m1, m2 over r squared. We can make this an equality if we put in a constant of proportionality, and that constant is called, I don't know how I got off center here, that constant is called capital G, or big G, not to be confused with little g, the acceleration due to gravity here on Earth, but this is big G. And the value of big G is 6.67 times 10 to the minus 11th, and that is the value of G in standard SI units. So we are going to multiply by a kilogram, divide by meters squared, and we want to end up with a force in newtons. So the units of G are Newton meter squared per kilogram squared. So when we multiply by 2 factors of kilogram, the denominator cancels. When we divide by 2 factors of meter, the meter squared cancel, and we end up with newtons. And that's just what we want. Okay, very good. So here is Newton's law of gravitation. This states that there is a force of attraction between any two objects, to be specific, any two objects with mass in the universe. So even these two pens, for example, would have a force of attraction. Well, why don't I feel that? Why don't I feel that force? Well, let's stick some numbers in here and see why. Let's calculate the force of attraction between two very ordinary everyday objects. Here I have a 500 gram mass, and here I have a 20 gram mass. So let's imagine we've got these, say, like this, separated here, and let's calculate what the gravitational force of attraction is between them. Well, we can measure this distance, and I put it at just about 50 centimeters, so half a meter. So we have that the distance from center to center is about 50 centimeters. So what's the force? What's the force of attraction? So it's going to be G, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, times M1. I'm going to immediately put these into SI units. So 500 grams, 0.500 kilograms, times M2, 20 grams, 0.0200 kilograms, divided by R, 500 centimeters, or in meters, 0.500 meters, squared. Multiply that all out, and what do we get? We get 2.67 times 10 to the minus 12 newtons. If we were to write that out, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 6, 7 newtons. I think that's right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. There we go. So why don't we notice this force? Because it is so incredibly small. The reason that the force is small, ultimately, in terms of the law here, is because G is so small. This gravitational constant is a very, very small number. And so, the attractive forces between ordinary, everyday type things is going to be very small, not something that you would tend to notice, in an ordinary, everyday sort of way. In order to get a force that is going to be something that really can be felt, typically, basically, one of these masses has to be very, very large. For example, the mass of the Earth. Well, in that case, if one of them were the mass of the Earth, then we definitely notice the force of attraction, because that is what we call the object's weight. The Earth attracts this 500 gram mass downward due to the attraction due to gravity, and we feel that force, or if we hold that object, we feel that force as its weight, and we call it the object's weight. We'll come back to that later and see how the object's weight here close to the surface of the Earth comes about using Newton's law in just a minute. Okay, great. So let's take this and let's apply it to Kepler's laws and see how Kepler's laws, well, at least some of them, in some respects, come about due to Newton's laws. Newton's law of gravity and his laws of motion.